talk is given by Leo Lee, and the title is Mind's Abstraction Gap, Bringing Equality Saturation to Real-World Machine Learning Compilers. Please start.
Okay, great. Thank you for the introduction. Hi, I'm Leo, and I'll be presenting some work we've done on bringing equality saturation to real-world machine learning compilers. So most of this talk is about the real-world bit, but to do that, we need to talk about equality saturation. And to do that, we need to talk about computation graphs. So in compilers, computation graphs are sort of data structure representing the mathematical expression that we're trying to evaluate. And the very common sorts of optimizations on top of these computation graphs are called people optimizations, where there's a bunch of these rewrite rules which state how a subgraph should be transformed into some other more efficient subgraph. So for instance, maybe we might change this a times 2 here into a left shifted by 1. It's a very common optimization to make. But a problem with these optimizations is that these are destructive. Once we've changed a times 2 to a left shifted by 1, we've lost information about the fact that this used to be an a times 2. So if we have a different rewrite that says, oh, actually, a times 2 divided by the same thing is actually just a, we can't apply that rewrite anymore because the times is gone. So this is called a phase ordering problem because the order in which these rewrites are applied turns out to matter. So equality saturation is a technique that was invented to sort of get around this problem, and it's in 2 stages, exploration and extraction. And so the exploration phase hinges on this sort of data structure called E-graphs. E-graphs are a bunch of E-classes, and you can think of an E-class as an equivalence class of E-nodes. And the main idea is that rewrites are additive. Once we apply a rewrite, or the first rewrite that we saw earlier, instead of taking away from the graph, we add to the graph. And so we have this new node that says, well, a left shifted by 1 should be in the same E-class as a times 2. And so because the original information is still there, we can apply the second rewrite and get out a, which is the simplest expression we can get. E-graphs are not perfect. So if we can, for example, consider this E-graph with a bunch of chained pluses and a couple of rewrites that say that addition is associative, then look, we have a chain of pluses there, so we can rearrange that. There's a chain of pluses here, so we can rearrange that. There's a different chain of pluses there. Oh, actually, that second plus was created by the first rewrite, and so on. So it might blow up sometimes, so it's not always scalable. So that's the exploration phase. There's also extraction, because we can't run an E-graph. So we need to extract out the best computation graph from that, and we'll have to do that according to some cost model, and we'll talk a bit about the cost model later on. Great, so now we can talk about real-world machine learning compilers. There's a lot of them in the world, but they all look quite similar, and today we'll be talking about XLA. So XLA is the compiler being used by TensorFlow and JAX, and there's also a PyTorch front end for it, and it's built on top of the MLIR and LLVM compiler infrastructure. And here's a bit of an overview of the XLA compiler. It's a traditional compiler with a lot of passes that are composed together. And this is in contrast to previous work that have tried to use equality saturation on machine learning compilers. They use toy compilers, where equality saturation is essentially the compiler. So back to XLA, we can take a look at one of the passes, the algebraic simplification pass. XLA is open source. You can just check its commits. And if you look, you'll see a lot of commits of this form. So this is a commit that adds an entirely new instance of the algebraic simplification pass before the constant folding pass, because it interacted better that way. So there's a bit of a phase ordering problem going on. Or this commit, which adds a condition to an existing rewrite in an algebraic simplification pass, because when that rewrite was applied, that inserted a copy in some copy insertion pass later on. So this is bad, because not only are there sort of these long-range dependencies between rewrites here and some other later passes, compiler writers need to sort of do this sort of reasoning per rewrite. There's a local heuristics thing going on, and this is not a very scalable sort of heuristic. So we can ask the question, okay, what can we do better? And equality saturation seems like the right hammer to thread the problem, so we can try. So of course, XLA doesn't use E-graphs. It uses stable HLO, which looks something like this. So values are sort of immutable tensors, and everything is nice, everything's pure, it's an SSA form. And it turns out that there's a nice mapping from this into E-graphs. And of course, as we apply rewrite rules, we can grow the E-graph in the natural way, and everything behaves nicely. So this is very nice. But we hit a wall very quickly because real-life machine learning models are big, and we've seen earlier that equality saturation might blow up. So we need to tackle scale somehow. And one way to do this is to make an observation that a lot of real-world machine learning models are composed of very discrete components. And not only that, a lot of machine learning models are straight-line programs, or it looks something like straight-line programs. There's not much connectivity between these components. So we can say, okay, well, can we just split the input into independent e-graphs and then apply quality saturation sort of independently and then combine them together? So that's what we call segmentation. And we lose some optimization opportunities by doing this, and in particular, ones that happen across segments. But as I said, because of this observation that there's not much connectivity between these segments, it turns out to work quite well in practice. And we've done some empirical evaluation on the segmentation heuristics that we use, and in particular the segment size, and we see roughly what we expect. So as segment sizers, as we decrease the segment size, then we lose a lot more optimization opportunities, so we get a lower speed up. If segment sizes are too high, then we hit into memory and time limits for the actual equality saturation procedure itself, so we don't actually do as well either. Okay, great. Now, back to XLA. So XLA has all of these great passes, and we would really like to keep them. So we have to insert ourselves sort of here. But this is a new problem, because many impactful transformations can happen after equality saturation. And to see why this is a problem, we need to talk a bit about extraction in equality saturation. So extraction, at the core of it comes down to when we have E-classes with more than one E-node, we need to sort of pick which one we want to have in the resulting computation graph and then sort of traverse down the E-graph. And how a lot of existing literature does this is by using an integer linear program. So you minimize a term that sort of looks like this, where sigma is the indicator variable saying whether a node is chosen. So 1 if it's chosen, 0 if it's not. And there's also the C term, which is the cost of the node. But now we're sort of making this unspoken assumption that the cost of the entire graph is the sum of the costs of the individual operations. And this might not be true. And a very concrete way in which this is not true is a thing called operator fusion. So at a very high level, we can think of computation or nodes in computation graphs as being individual kernels that are being dispatched onto the GPU. But their data needs to end up in the right place. So there's some sort of bookkeeping that the CPU needs to do and some data transfers. And we can think of the edges as data transfers between that boundary. And a common sort of optimization is to get rid of those data transfers by fusing the kernels into one big thing so that everything stays nicely within the GPU. But of course now, the cost of that fused multiply add kernel is not going to be the same as the cost of the add and the mul added together. That's the entire point of the optimization. And so our assumption breaks, and our cost model should be aware of this. And to do that, we add this fusion bonus term to the term being minimized. So for a given producer-consumer pair, we can estimate how much XLA can save on the sort of data transfer costs by fusing the kernels together. We can add that to the term being minimized, and essentially that's using the cost model to push extraction into picking nodes that are more amenable to fusion. So if we sort of step back and think about what we're doing, we're replacing local heuristics with global ones. For each rewrite, we don't really need to care about how that will interact with later passes later in the pipeline. We can just let the exploration phase, explore, and let the cost model deal with picking, having all these heuristics and picking the right rewrites or the operations resulted by the right rewrites. So we can briefly discuss results. We've evaluated our procedure on a wide range of models. There are some machine learning models, some are not. For example, there's a molecular dynamics simulation somewhere in there. And the dotted purple line is the baseline, so that's what happens if we just run JAX on XLA. The blue is enzyme JAX, which is an implementation of a bunch of rewrite rules, but in a more traditional fixed point-based applier. And there's the green is us, Constable. That's the name of our quality saturation pass. We can see that we do quite well on CPUs. We have up to 56% speed up on a Threadripper. I'd also like to draw your attention to this. So it turns out that enzyme JAX has some rewrites that interact badly on that architecture in particular. And so in a traditional compiler, to sort of avoid that sort of regression, we would have to go through the rewrites and then add a condition to say, please don't trigger if some condition is met. We can just avoid that because the cost model is aware of the cost of the operations. And we can just not pick the operations produced by those rewrites. So some conclusions. So by carefully managing heuristics, we can get the best of both worlds. We can harness the power of equality saturation and the sort of pseudo-exhaustive search that we get, but while taming its computational requirements. And we can do this in front of some other traditional compiler passes, but as long as the cost model is aware of everything that happens afterwards. Thank you.
So perhaps I misunderstood something, but as far as I understood, you do not actually perform diffusion, but rather you have a cost model that says, hey, we favor stuff that is amenable to fusion. Why don't you perform diffusion as part of a rewrite? Because I would have thought, hey, eGraphs are perfect for this.
Future work.
Yeah, there seems to be a lot of fusion opportunities that we would like to explore that is even harder to scale than the sort of existing set of rewrite rules that we have. So we would like to explore that as future work, but this is what we have so far.
Okay, thanks.
Any other questions?
Hi, thanks for the talk. Could you tell a bit more about segmentation, maybe? Do you have some heuristics that guide which part of the program you segment?
So as Leo mentioned earlier, we have some heuristics that guide segmentation. In particular, we make the observation that a lot of machine learning programs and things that we feed into the equality saturation pipeline have this sort of linear structure. And in particular, this means that it's very unlikely you have long-range dependencies between the very first instruction and the very last instruction in the program. So by making this observation, we kind of minimize the number of optimizations that you lose that are crossing the segment. Of course, there's very sort of complex heuristics that can be done here. I think past work like Metaflow by Phitchaya does a flow-based segmentation of the graph, but we found this to be unnecessary because this sort of linear segmentation gave very strong performance.
Okay, thanks for this response.